Okay, so chapter 5, if you're watching this in video form, it's better to work from a page of notes. Instead of filling this whole board up with notes and then erasing it and probably putting some more notes up, I'm just working from a handout. So if you like this handout, you might want to obtain the handout before watching the video. But we're into chapter 5, and a transition is happening here. Chapter 5 is going to be about a thing called integrals. What we've been doing for a few chapters, well, chapter 1 was an algebra review, chapter 2 was limits, chapter 3 and 4 was all about derivatives. So what derivatives have been about are rates, should be a familiar word, slopes of a tangent line, and there was a crazy formula with limits and stuff working in the background that let us find derivatives. If you remember a thing with like x plus h's and stuff like that. But what that's let you do is find velocity if you know displacement, find acceleration if you know velocity. We found a lot of things with rates and slopes. That's what we've been doing. Then there's a break, and we switch gears, and a transition happens. And now we're going to try to do things like, instead of finding v if we know s, we're going to try to find s if we know v, or try to find v if we know a. And instead of slopes, what we're worried about is finding areas under a curve, and sometimes finding volumes of solids. You guys had physics already this year as we're filming this here live. Other years you might not have had physics. You might be in physics concurrently with calculus. But there's a chapter in physics where we do a lot of graphing stuff, and what we did was found a lot of slopes of things, but we also found some areas under things at a point in physics at one time in our physics life. So if you wanted to find the area under a curve like the one that I drew there that I didn't draw on the board, that I'll draw on the board now, I guess. If you had something like this, and it has a beginning and an end, and you wanted to figure out the area under there, you can just use geometry to do that. And I think there's a little bit of homework in this chapter where you will basically just use geometry to find areas. Do you have a thought on how you could use geometry to find the area of this? Split into a rectangle. You could. You could do a split line this way, and you've got a rectangle bottom, you've got a triangle top, and just deal with it. If you're into obscure geometry facts, what shape is this? That's not an obscure geometry fact, but because these are parallel. I don't know what that's called when you got two of them parallel and the other two just do whatever. T word. TR. TRA. Trapezoid. At one point in our geometry life, we did areas of trapezoids with a formula. That may be long gone. It's been a while since we've done it. But we could get back into that another day if we need it. If we want to find an area under a curve like this, and now it's time for me to stand up, if I wanted to find this area, you can't really use geometry to do that. There's no way to use geometry to get an exact area for that. But if you partitioned it, which means you cut it into pieces, if I cut that into two pieces, those aren't really still very much of a familiar shape. If I cut it into four pieces, each one of these is starting to look a little bit more like a rectangle. And then you have choices as to how you could manage these rectangles. But we could cut this up into a bunch of pieces. The lengths would be determined by us. The heights would be determined by the formula. And we could just kind of do like width times height on all these rectangles through the world and get a decent guesstimate on that. So here would be a decision we'd have to make. This rectangle, you could act like it's that tall and work from left to right. if I cut that rectangle there, I should cut this rectangle here. I should cut this rectangle there. I should cut this rectangle there and have something that looks about like that. When I'm looking only at this rectangle, I'm a little bit too short. I'm underestimating because I cut off a piece I wanted. But here, I'm overestimating because I'm including a piece that wasn't really there. Right? Here, I'm low with my guess, but here I'm high with my guess. And I would just hope that over time, those would sort of balance out. So I could work from the left side. What would be another thing I could do to guesstimate these heights other than working from the left side? I can work from the right. So here, that's a little bit too small compared to reality, but that one is too big, and maybe it balances out. This one's too small, but that one's too big. So we could work from the right side. What would be another thing we could do to kind of self-balance it? Working from the right and working from the left, where else could we work? Right up the middle. I could go right up the middle to there and put a cap on it. And within each rectangle, I excluded something I wanted, but I included something I didn't. And those areas are probably about the same. It's probably close to a wash. So I could go up the middle, put a cap on it, and I'm both including and excluding at the same time. Go up through the middle, cap it, go up through the middle, cap it. Are any of those going to give us a perfect answer? No. Would our answer be better or worse if we did more shapes? Better. But it would also be more work. So let's turn a page. Question from page 1 from concept. Okay, so the sum of these areas would look like f of t1. Okay, anytime I have f of something is like synonymous for y. Like y versus f of x, those are synonymous. So if I'm saying f of t1, that's going to be a height from the first part. Some of the homework, that'll be given to you in a table. Some of the homework, that's going to come by plugging into an equation to figure it out. Some of it's going to just be by looking at a graph and guesstimating it. If I go back to this graph and I'm numbering like 1, 2, 3, 4, 5, 6, 7, 8. If I'm working from the left side, I might guess 4.5. If I'm working from the right side, I might guess like 7.5. If I'm going up the middle, it might be like 6.5. Okay, but we need a height from somewhere. The heights come from somewhere. Either a graph to look at, an equation to plug into, or maybe a table that's given to you. And then these delta t's just refer to how wide each piece is. Each piece is going to have the same width. So we need to go height from somewhere times width. Height from somewhere times width. Each rectangle, a height times a width, a height times a width. And when we're done, we want to add these all up. So I drew these little arrows on the notes page. Like f of t1 is just the height of the first one. F of t2 is the height of the second one, and so on and so forth. And we just decided that if we did more of these, it would be blank work. More work. But it's also more accurate. So then for some reason I'm looking at the top of page 271. So I guess if you have a book, head to the top of page 271. So I'm just reading the thing before the chapter starts. It says the formula D equals RT, distance equals rate times time, for calculating distance traveled, can only be used if the rate doesn't vary over time. If the rate does vary, we have to find the distance some other way. Like if you got in your car and you set your cruise control at 50 miles an hour and you traveled 6 hours, the distance you go is just 50 times 6, you went 300 miles. But if you're constantly on and off the gas and you're driving 50, 51, 49, 48, slow down to 40, back up to 60, down to 10, you stop, start. If the speed is changing, that formula goes out the window. You can't do that anymore. That formula is a goner. We'd have to find the distance some other way. One way would be to partition the time interval into short time intervals on which the rate remains fairly constant. Figure out how far you went when you were going 51. Figure out how far you went when you were going 49. Figure out how far you were going when you were going 10. And then add them up to estimate the distance for the entire trip. The more finely you partition the time interval, the better the estimate would be. So if you went on a trip and you're trying to figure out how far you're going and you're doing it based on your speed, if you checked your speed every hour, it's probably not that great. If you checked your speed every minute, that's pretty much going to get it. If you checked your speed every second and did math every second, it would be pretty much getting to be close to perfect. But the present chapter is going to explain the idea of estimating a final result by summing a finite number of close estimates made with standard formulas is the key to measuring all sorts of things. The new calculation formulas to which these summations lead, which will be called integrals, are the formulas which we find surface areas, mass, length of a space vehicle's trajectory, future size of a population, the amount of work it takes to move an object against a force that varies with time or position. The mathematics of integrals is called integral calculus. Our shift from derivatives to these finite sums and integrals may seem abrupt at this point, but the two are closely connected. The nature of this connection is the most important idea in this chapter, and the discovery by Leibniz and Newton still constitutes one of the greatest technical advances of modern times. So they're typing this up for you. What's the word finite mean? It has an end. It's countable. Okay, so it's the opposite of infinite. Something infinite is not countable. Something finite is countable. So you'll hear through the chapter different points. They'll talk about finite sums, meaning we're going to add things up, but not endlessly. The best way to do this would be really to cut it into an infinite amount of pieces and add them all up. That would be the most accurate way, but I mean, good luck with that. That's kind of what they will eventually have in mind is, what if instead of adding up 4 pieces or 8 pieces or 16 pieces, we had an infinite amount of pieces to add? That's where they're going. Let's flip a page. Let's look at example 1. So example 1 says there's a velocity function of a projectile fired straight into the air. It's 160 minus 9.8 t. Use the summation technique we just described to estimate how far the projectile would rise during the first 3 seconds. And then let's see how close we are to the real answer of 435.9. So here would be your first thing is decide how many pieces you want. So if they're doing something for 3 seconds, how many pieces would you feel like probably? Probably 3. Okay, so we'd work from 0 to 1. We'd work from 1 to 2, and we'd work from 2 to 3. So then the question would be, what number do you want to use? So they worked this problem 2 ways. They decided first to do left-hand endpoints. So if you want to use the left-hand endpoints, you'd use the 0 or 1, which one? If we want a left-hand endpoint, use the 0. And for this group, use the 1. And for this group, use the 2. Okay. So if we're going to go and do left-hand endpoints, we'll use the 0, the 1, and the 2. We need to use that 0, 1, and 2 somehow to decide on heights. Okay. A few minutes ago, I told you sometimes you figure out the heights from looking at a graph. We don't have a graph. Sometimes they'll we'll want to figure out the heights by looking at a table. They didn't give you a table. So the third way we can figure out the heights is by plugging numbers into an equation. So what we need to do is take the 0 and plug it into an equation. If you plug 0 into the 160 minus 9.8t, it'll give you out a 160. Then for the second group, you plug in 1 and you'd get a 150.2. The third group, you'd plug in 2 and you'd get the 140.4. Then what you could do at each phase, you could go at each phase times the width, times the width, times the width, times the width before you'd add them up. But realistically, if all the widths are the same, you don't have to multiply at every phase and then add. I think it's quicker to just add up the numbers and multiply once at the end, just as a math saving time. So if we add these numbers up, we get a 450.6. And then how wide are all of these? Counting by ones. So we'd add the stuff up to the 450.6 and then multiply by 1. If I wanted to be more accurate, I would do 6 cuts. I'd make each one half a space wide and do 6 cuts and add up what we got if we had 6 cuts. But I'm not going to take us through the steps of that because it's just sort of tedious. That's a possibility. Another possibility would have been use the right-hand endpoints. If we're using the right-hand endpoints, we plug in 1, 2, 3. If we want to do the right-hand endpoints, we would do the larger numbers. So I did the math on this that way. The 1 plugged in we knew was 150.2. The 2 plugged in is 140.4. The 3 plugged in we can discover is 130.6 if we plug in. But again, like last time, add them all up. It's 421. Multiply by how wide. It's 1 apiece, and we're good. Question about how that math happened? As a what if I did 6 cuts, and I didn't make this all. If I wanted to do 6 cuts, it would be going like 0 to a half to 1, and so on and so forth. For the left hands, we plug in all 6 of those into the formula, and it ends up being 443 on the notes sheet. For the left side, it ends up being a 428 on the right side. The real answer is 435. So you can see the more cuts you do, the more work it is, but also it got closer to being the real answer. Question about how that math sort of went. And the next thing this says is we should look at 278 homework number 1 together. So 278 homework problem number 1 together, they're giving you a table already. So what the times are going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're not really going to worry about those numbers other than to notice that they're counting by ones. So after you're done with your math, you multiply your total. Once you add up a bunch of stuff, you'd multiply by 1. Just ones. But what you're going to have to do is add up the correct numbers. You're not going to add up all the numbers for the velocities. If you want to do the left-hand endpoints, you'll add up most of them. Who won't get added if we're doing the left-hand endpoints? If we're going to add up left-hand endpoints, who doesn't count? This problem we just did a second ago, we had 0, 1, 2, and 3. When we did the left-hand endpoints, who doesn't count? The 3, the highest one. If we do the right-hand endpoints, who doesn't count? The 0, the first one, the lowest one. Okay, so what you're going to look to do on homework problem 1 is add up all those velocities. For the left-hand endpoints, don't add the first, or don't add the last one. For the right-hand endpoints, don't add the first one. And once you add them up, multiply by how wide they are, which was 1s. So on 2, you do about the same thing. You look at the 0, 5, 10, 15, 20. That's only there so you can see how much it's spaced by, which is 5. So what are we going to do with that 5? Multiply it at the end. What we're going to want to add up are the numbers from 1, 1.2, 1.7, 2.0, add up all those numbers up to 0. But when you do the left-hand endpoint, you don't add in the 0. When you do the right-hand endpoint, you don't add in the 1. Question about concept on that? And here's a weird thing about the units. What's weird about the units on 2 that they messed with you for reasons that I don't understand? It's minutes versus seconds. So how could you adapt that to be a more consistent thing? Correct. Multiply all the minutes by 60. So don't at the end multiply just by 5. Multiply by 5 and by 60. Or by whatever 5 times 60 is if you want to do it that way. 3 is still the same. Okay, so 3, if you want the left-hand endpoints, you don't add in the 35. If you want the right-hand endpoints, you don't add in the 0. You'd add up all those other numbers though, and when you're done, you'd have to multiply by. You good with 1, 2, 3? Then we're looking at an example 2. Example 2, the notes say table on page 274. That should say graph on page 274. So the example 2 connects to the graph that's to the left of example 2. When it says find cardiac output, we're trying to find the area. So what they did is they have this blue graph and they put these red caps on it. Did they do the red caps from the left, from the right, or by going straight up the middle? Are they extending from the left of each rectangle, from the right of each rectangle, or did they like track right up through the middle to put a cap? They went right up the middle. So, like the first rectangle, if you can imagine, like finding with your pencil the 6 mark, and then tracking your pencil straight up till you touched blue. That's where they drew the capper. You know, from 7 to 9, imagine touching your pencil on where the 8 is, tracking directly vertical until you touch blue. And as soon as you touch blue, put a capper on it. That's what they did on those. We're going to use the heights from the graphs at the midpoints. It's more accurate than using the left or right if you go up the middle. So from 5, the first cap, that first red hat that's connecting 5 to 7, about how high does that look to you? Let's go decimals. Yeah, I would say, I might have said 1.4. You said 1.3. When the book did theirs, it looks like they used 1.2. So there's going to be a little bit of variation in these because we're just kind of guessing. It's definitely under 1.5, but I don't think I would go 1.2. That feels low. I'd say that's in the 1.3, 1.4 range, but there's going to be some variation on this. From 7 to 9, about how high does that look? Yeah, 6.2, 6.3, I'd say. It looks like they're doing 6.8, and I don't understand how they're saying that's 6.8. Like, that feels like a lie to me. But we'd go through and we would generate those numbers from looking at the graph. Are you with that, Chief?
Yeah.
Okay, so then we'd add up all those numbers, and then what would we multiply by? 2, because they're like 2 wide. But that's not, we're going to have some disagreement with each other on that. Because some of them we're going to guess low, others we might guess high. You hope it just sort of evens out. Okay, so let's look back at homework page. For number 4, don't use the table. Ignore the table. Look at the graph. They want us to use the graph and the midpoints. What I would do is I would consider the .002 to be the end of a first rectangle. And then I'd use the .001 line that's unlabeled. I'd use that line as my midpoint line. And my first height I would use as the 40. And then I'd look at the .004 as the end of the next zone. I'd look at the .003 line to help me track up to a height. And I might say the .003 line is maybe like 83. Because I don't believe that's flipping that corner. I think that's a little bit above the corner. You understand what I'm doing there?
Yeah.
So we'd add up a bunch of those, and then we'd multiply by how wide each piece was. Based on my choices, how wide was each piece? .002. I was tracking up the .001 line because that was the midline on my way to .002. So I would look at that as 5 zones with 5 midpoints, add up 5 heights, multiply by .002. 5, same kind of thing, okay, but 5, I would just do 12 pieces, like 2, 4, 6, 8, 10. I'm looking at those numbers as the beginnings and ends of my zones, and I would use the odd unlabeled numbers to guesstimate heights. So like from 2 to 4 is my first zone. I would put my pencil on where the 3 is. I would track straight up, and I would feel like that might be .6, I don't know, 0.5, 0.6, something like that. 0.55 if you want to get fancy. I mean, I don't know what you want to do there, but you know, we'd add up a bunch of those heights, and then when we're all done adding up, we'd multiply by 2, because they're all 2 wide, but I'd have like 12 of them to add. Number 6, you get to make your own graph. So what you want to do on 6 is, I'll lend you a piece of graph paper if you don't still own graph paper. For 6, you'd make your own graph. I would count probably, you're going to be more accurate if your graph is bigger or smaller? Bigger. So what I would do is probably count on the x-axis by 1. I face the paper this way, and we need to cover 30 squares this way if we count by 1s, and that's how I would count, because you should be able to fit 30 squares across on a piece of graph paper. So I'd go 1 square piece, 30 squares across. To go vertically, I don't think you have, let's see, your highest number is 79. I don't think you have 79 squares on a piece of graph paper. So I wouldn't count by .1s, it won't fit. I'd probably count by .2s. Because again, bigger's gonna be better. So I would do a nice big graph that goes by 1s on the x-axis and probably by .2s on the y-axis. You only want to graph a quadrant 1. So I mean, you could use the edge of the paper as your x and y axis, or you could draw your own x and y axis, like 1 square in. But you're going to play the same game on 6 that you played on 5, same game that you played on 4. Just on 6, we're going from 0 to 30 by 2s, so you're going to have like 15 numbers to add up. This homework is more tedious than it is like heavy math involvement. It's just a matter of trying to do what they're explaining to you is, you can't figure out the area the way it is, so you cut it into pieces, you add up all the pieces. From the tables, they have you using the left. From the tables, they have you using the right. From the graphs, they have you using the midpoints. They don't have you at all today plugging into any kind of an equation. Okay, but those will be the 3 options through the chapter. Is the widths will be because you chose them, or the book chose them. The heights have to be found either from tables, from looking at graphs, or from plugging into equations that could go all of those ways. The homework's 1 to 6.